start. Should I introduce the Chinese or the English?
It's up to in German.
Guten Tag. We are very pleased. Very glad to have Dr. Ashley here. He has been invited under the GFR. GFR is the NCU GPS GFZ Research Center. He actually is invited for more GFZ research. And he already gave a talk. And this was space science. And this is his day here, the last day. Tomorrow he has been here for Germany. So we take this opportunity to ask him to give another seminar in this department again. Dr. Next week has been here for many times, how many times?
I think I'm here the eighth time now.
Really? 8 times.
So I have frequent travelers. That was to Taiwan.
Great, and I saw the Vita here. He actually was he got a PhD in meteorology and geophysics at the University of Graz, which is located in Austria. Austria 的一个气象的技术的PhD in 2002. And but he graduated, he got the master's degree at earlier time. He has been working for many years. And he is actually the very special scientist on the GPS data retrieval and center GFZ.
In German we say GFZ. GFZ. Geo-Forschungszentrum. But for you it's maybe more easy. Geo Research Center.
Yeah, so something like the Geo Research Center, similar to our GPS app.
Yeah.
And today we are also very glad our team can attend this seminar. And this is a very special arrangement for our students. You guys are going to introduce the GNSS is some kind of the combination of the GPS satellite. This satellite can use the remote link with LEOs to obtain the atmospheric soundings. And this kind of sounding can provide a lot of information about atmosphere. And Dr. Ashley is going to give you an overview and the recent results, and maybe has some suggestion for the Taiwan side where we should go, and maybe we can set up some official collaboration between Germany and Taiwan. Okay, that's where Dr. Wickert.
Thank you very much for this introduction. And I'm a bit sorry about this small delay because I waited in the other room for you. And I was wondering, nobody was there, so I thought, oh, no interest in my talk, so I should give up here. So, but of course, I'm very happy that some more persons are here now. And I'm also happy to learn that I'm the second person from Germany in 2 days. So yesterday, Professor Warner from Forschungszentrum Jülich was here. And so we have a very close cooperation in Germany because we are from the same research program, Atmosphere and Climate. They participate Forschungszentrum Jülich with Professor Warner is responsible, Forschungszentrum Karlsruhe, also from southern Germany, Professor Kottmeyer and my person from GFZ Potsdam. So we participate in the same research program with these 3 institutes. But today I want to give you some overview on our activities on GNSS atmosphere, atmospheric research, not only space-based research, so you know about the CHEMP satellite, and you of course have your Formosat satellite. We also do some ground-based activities, but we also have some activities regarding the future. And I want to give you some overview on this, what we do at GFZ. So I would like to first introduce GFZ Potsdam as a general, as our institution, and more detail to the ground-based sounding, then characterize our space-based activities, Also some remarks on Ionosphere activities which we started recently, and one thing for the future is reflectometry. We have some significant effort also in this. Of course, first of all, I'd like to thank you very much. First of all, my host here at NCU, Professor Wang. I'm very grateful to him also for organizing all these things with an invitation. I also would like to thank GPS Arc, which funded the stay here. And this I showed already in my last day in 2006. So I saw this sunrise live, one can say, at Alishan. So it was very early in the morning. I think it was 4 o'clock or so in the morning in October 2006. The sunrise at Alishan.
You have been a Yangmin Mountain Peak.
I was there, and this time I was at the Yangmin Peak, and I also, of course, I had a lot of travel during my during my 8 days in Taiwan. I enjoy it every time very much to be here, and I'm also happy to say that I come back in October for the School on Atmospheric Research. So I'm also invited there to give some talks, so in total 4 talks, and in addition also this Formosat 3 workshop. So GFZ Potsdam is my home institution. Of course, I'm back. I'm also happy to go back tomorrow to Germany, and I will work on Monday, the first day after the long period. Potsdam is located here in the heart of Europe, very close nearby Berlin, and we have a long history of geo-research at the Telegrafenberg. This is the Telegrafenberg. It is a hill not so far from the main railway station, and we have geo-research there already more than 100 years. It was started in 130 years ago. This is a view to the Telegrafenberg. Telegrafenhill is the translation here at 1892. We have a lot of historical buildings here. The Geodetic Institute, which is a home institute of our activities. We have the Astrophysical Observatory. We also have Magnetic and Meteorological Observatory. For example, here is one of the longest climate temperature records. This home is taken here at the Telegrafenberg. It is longer already than 150 years. So we have a long history on geo-research at the Telegrafenberg. Now it looks a bit more different. We have much more trees here. But you see also these historical buildings are kept in a very good shape. Here again the Astrophysical Institute, but our home institute here is an institute for a department for geodesy and remote sensing. So this is a view to Potsdam. Potsdam especially is also a very nice place to live. We have a lot of water here, a lot of parks, and it's really a very nice place to live. Geoforschungszentrum is funded by the Federal Ministry of Education and Research by 90%. The remaining percent are coming from the Ministry for Science, Research and Culture of the state Brandenburg. So probably you know that Germany is a federal republic. We have 16 different states. Brandenburg is one of them and contributes to our funding by 10%. We are a quite large institute, so we have increasing number of personnel. Currently we have 855 persons. Maybe it differs already by plus minus 10. This is from May, these numbers here. We have 110 PhD students. The budget is 44 million euro per year. But also we have from these institutions, but an increasing part, currently 35 million euro comes from third-party funded projects. This means this money we have actively to promote. So we have to write proposals to get this increasing share. This share is increasing, and this is also a tendency that the share of third-party funded project is more and more increasing, but this is also allows us to react flexible to trends and to recent trends in research. So we have some structure here. We have 5 departments. Main department for our activity is the Department for Geodesy and Remote Sensing. We have GPS Galileo technologies. This is our section. Earth observation satellites, gravity field. a lot of activities. Professor Chow knows more details on this. We have remote sensing. It's a visible range here of radiation, Professor Kaufmann, and also some new section Earth system modeling. But we have also other departments here: physics of the Earth, geodynamics, chemistry of the Earth, and geoengineering. I don't go to the details here. If you have questions to this, you are invited to come to me or to visit the web pages here. So, but the focus here is atmospheric sounding using GPS. And we know about that GPS is a story of success, especially for positioning. But we have currently an international tendency that these data are more and more in use also for remote sensing, not only of the atmosphere, but also, as you have activities also here in Taiwan for GPS seismology, for example, which we also can put to these remote sensing activities. Two important dates for this: in 1995, the GPS system became operational, and in 2006, atmospheric data derived from GPS are operationally used from the various weather centers to improve numerical weather forecast. For example, also the Formosa 3 data, also our SHAMP data, but also ground-based data. These activities started operational in 2006, and this is a new dimension for the use of GPS data in atmospheric remote sensing. What we do at the end, we use the influence of the propagating medium to the GPS signals to derive characteristics of the atmosphere. This is, of course, the bending is an error for the positioning, but this bending is our signal if we do atmospheric remote sensing. From these bending angles, or from series of bending angles, we at the end derive our vertical profiles, and as a excess phase bending, excess phase delay, for example, for the ground-based station, is used to derive, for example, vertically integrated water vapor values. A new development is currently in more and more progress, that we derive characteristics of reflecting surfaces from reflected signals. I come in more detail to this. This is a new development. Multipass, of course, is an error for the precise navigation, but it's again, it is here our signal source for remote sensing to derive characteristics on water and ice surfaces. Ground-based sounding, it's the first topic here. We use the signals of GPS satellites to derive vertically integrated water vapor. We do this on a global base using a network here of about 200 stations, which is part of the international IGS network, International Service for GNSS. We use a global network here. Data are available since 1993, so you have already data for different climate zones for more than about 15 years. In total, about 160 stations, and you can use these long-term data to derive first climatological information on variations, for example, of the water vapor. There are several publications in the pipeline, but if you are also carefully look to GRL or GGR, there are several publications that have this data set as the main focus. We derive the integrated water vapor with an accuracy of about 1 millimeter. As you can see here, the most of the colors is green or light blue. This is 1 millimeter accuracy. So if we know that in maximum we have about 40 millimeter vertically integrated water column, then it's an accuracy of about 5%. We also do this regionally densified with a network of 230 currently stations in Germany. We plan to extend the density of this network up to 340 stations still within this year. We operationally process these data and provide the water vapor information in near real time. This means this maximum delay of data provision to the measurement of about 1 hour for several international weather services. So one example here, we had a large storm Kyrill in January 2007. It caused several damages here, and also a lot of trains were cancelled. So we could provide for this storm, for example, a very spatial and also in time very high resolved water distribution. So you see here coming from northwest, so the most weather in Germany comes from northwest. Here you clearly see with a very high time resolution of 5 minutes. You see here the water vapor modification. So you have no other measurement technique provides you water vapor information with such high resolution in time, and here also in space if you have these 240 stations.
How real time is this?
This is not real time, but we provide this data in real time, continuously, day and night, with a maximum delay of 1 hour. And this is
into the operational model?
Yes, and this is used currently, and this is this plot here. The data are not only for showing videos also, they are in real use by, for example, Meteo France and also Met Office since 2006. We are in preparation, we are very close to operational assimilation at the German Weather Service, and as I understand also there are some activities from ECMWF also to use these ground station data, but their focus is global. Here, these data are more assimilated for regional models. So we have a database for this assimilation. The green dots here are German stations which has some major share in this data which are assimilated. We also have significant activities here in Switzerland and also in UK. Less data are provided in France and Spain, but you see there are several activities, and we are currently also have activities to increase this number of GPS stations used for the weather forecast. So another activity which we started beginning of this year within within a research project which is funded by the German Research Foundation. We not only use the vertically integrated information, we also use the slant information to various satellites. This at the end allows us to include also information on horizontal distribution of the water vapor and base at the end for three-dimensional reconstructions of water vapor above Germany. So what you do at the end as a computer tomography of the human body, you pixelize your volume here, the atmosphere, a 3D voxel structure, and then you use the different links to calculate at the end the water vapor in this voxel structure. And we have some, and what we do, what our goal is at the end to derive three-dimensional humidity distributions above Germany. Here is an example. Here are the Alps. This is northern Germany. This is southern Germany. And this is the goal of this project to derive three-dimensional water vapor data. This is done here with a model data, regional model data, but we have already first results of this three-dimensional water vapor tomography. This is a horizontal slice above Germany, only GPS data, reflectivity, the wet reflectivity which can be related to the humidity at 500 meter. Because we have a three-dimensional distribution, we can of course show a horizontal slice. In the first, this is the first shot. Initial results very quick. Only 6 months ago we got these. We started these activities, and this was the first result from about 2 months ago. What we see by quality, we see already a quite good agreement. So we have much of water vapor here in the model. We also have it here in the tomography. But what we also see, we have some artifacts here probably related to the non-equal station distribution here, for example here. So here is probably an overestimation of water vapor by the tomography, but in general for a first shot I think it is very good by quality. It also agrees here a lot water vapor, less the water vapor, agrees also very good with our plots from integrated water vapor. So it is a three-dimensional distribution. This also means we can do vertical slices here, and this is also compared from the Cosmo model with the tomography reconstruction. Red is a lot of water vapor, yellow is here less water vapor. We also see in general the structure given here by the model is very good given. But of course, at the end, we also want to improve the model. We not only want to compare with the model and say, okay, we are in quite good agreement with the model. Our final goal is also to improve the model. This also would mean that these data should be assimilated to these models. So, and we also can do compare vertical profiles up to 10 kilometers given from the tomography with the Cosmo DE model, and what we also see here, and for this first reconstruction we have very good agreement, but if we look in more detail, we of course also have some deviations, but this project will be continued until 2010, and of course we hope to get additional money. But our first results indicate that this is some very good potential here for the future. I know also on such activities in GPSR, there are at NCKU some activities, and we have also some conversation on the probable cooperation on this. So, and the goal of course is to provide three-dimensional water distributions based on GPS measurements with a high time resolution. Again here, a significant storm event above Germany and a model simulation, but of course in 2 years I show such simulations based on GPS. So the future outlook, of course, we are very close to have much more satellites. That's why also the talk, the title of my talk is not GPS atmosphere sounding, it's GNSS. GNSS means Global Navigation Satellite Systems. GPS is only one of them. We only have Galileo. Galileo will come. We had a half year ago, we had a final decision that this will be funded by the European countries, by public money at the end. This will be about 2012. So we will have, and we also will have reactivated the Lunar system, the Russian navigation system. That is they put more money to the system to reactivate. We also have an increasing number of Lunar satellites. So if we work with the receivers which can receive all these three navigation satellite signals from all these three systems, we come at the end to use signals of 90 satellites. So what we see here, it's a distribution, the number of slants over the azimuth, so over the entire viewing angle here of the GPS antenna. We will see that Galileo, the green line, will provide nearly the same number as currently provided by the GPS satellites. This, of course, is a great perspective also for GNSS remote sensing for these three-dimensional reconstructions, but for all related activities here. This is another distribution here for different elevation angles. So you see also for low elevation angles that we have more data, but also Galileo green line here provides nearly the same data as GPS. GLONASS, we still have about 15 satellites, so it's slightly less, but we expect to have more satellites in the near future also for GLONASS. Space-based sounding, you know about radio occultation. I should not put here too much detail. So at the end we use the bending angle, which we can measure with the GPS system with very high accuracy. We use the time series of the bending angles to come at the end to vertical profiles in the neutral atmosphere. This means temperature up to 50 kilometers, water vapor in the lower troposphere up to about 10 kilometers, but also electron density here from about 100 to 600 kilometers. Key characteristics: global coverage, all weather, calibration-free, high accuracy, and all such things, high vertical resolution. You know about these things because you have a great Formosat 3 cosmic mission here by US and by Taiwan, of course. But we have also some activities, so you know about our CHEM satellite that was launched in 2000. We have a great satellite. The main mission goal here is gravity, of course, but we also have occultation antenna, which enables us since 2006 also to get occultation data from the GRACE satellites. And we also have two other satellites. Karazhan X launched last year. We have a GPS receiver aboard, but also Tandem X in 2010. Also GPS receiver for occultations hosted by GFZ. Cosmic, Formosat 3. I don't have to talk so much about, you know much more better on this mission. We also have a European mission, METOP, a very large satellite, a lorry size-like satellite. We have a European GPS receiver here since 2006. CHEM provides first long-term data set, and if you look, again I tell this through GRL or GGR papers, there are a lot of investigations currently related to this long-term data set. Of course, Formosat 3 provides much more data, but COS-CHEM is the only data set which covers now nearly about 7 years. So a lot of investigations of climatological relevance can be done with this data set. This data set is extended currently by GRACE, which provides nearly about the same daily number of profiles compared to CHEM, and GRACE will last a bit longer until 2012, 2014, and will extend this long-term data set from CHEM, which also, of course, will be completed by the Formosat 3 missions. This is our new collegiate space, Karazhan X. It was launched last year, so it's also a quite large satellite. It's 1.2 ton. CHEM is about 400 kilogram. It is much smaller. And radar, Karazhan X is a radar satellite. So they have a radar which scans the Earth with a resolution of about 1 meter. So an example here is one of the first pictures taken by Karazhan X. These are the pyramids in Egypt, in Giza here. So this is impressive initial results, but we also have a GPS receiver. It's an IGO receiver by Broadreach. The same receiver is used for Cosmic, and we also use the same occultation antenna here for Formosat 3. It is working on Karazhan X. But we have some problems, I would say, because we have not appropriate funding for the occultation here, and also some complicated contract structure, which make it at the end difficult to get at the current moment occultation results, so I cannot show you too much on this. But we have already had a demonstration here for the operational orbit determination. And the orbit accuracy is about 2.4 centimeter for Karazhan X continuously, and we got this result here by comparisons with laser data. So the prospect is that Karazhan X will not stay so long alone. We will have Tandem X, the second satellite. I showed this already, which is the same satellite, so a one-to-one copy of Tandem X, and this will enable, as with your eyes, you observe with your eyes, to look to the Earth surface in 3D. So this will be the deeper reason that we will have very soon a second satellite, Tandem X, which will complement Karazhan X to get three-dimensional view to the Earth surface here. And for us, of course, for the occultations, this would be also a very good opportunity for calibration of occultation missions. If we have both satellites which measure at the end the same occultation volume, then we can derive at the end influence of ionosphere and all these things. This is also a very interesting constellation for occultation. Of course, you know, on Formosat 3 and cosmic mission, only in brief our activities, we have no plans for operational data analysis, but we have, of course, the ambition for a complete process from the raw data level up to the profiles for selected periods. We have complete orbit results for all 6 satellites here in 2007 for day 2016 to 216 to 219. We also have initial results of open loop processing, and we use UCAR analysis results for various applications. I come back in more detail later. Tropopause, gravity wave, and sporadic E investigations. Here one example of our orbit results for Cosmic 2 satellites. Here are the values for the comparison with the UCAR results. 16.3 centimeter, for example, in this 3D comparison with the UCAR orbits, and the velocity deviates here by 0.2 millimeter per second. These investigations also help to improve the orbit quality of the UCAR results. And we show here in comparison for the radial component of Cosmic 2 satellites. So this is the difference here between UCAR and GFZ solution. Mean deviation here is 3.8 centimeter, RMS is 9.4 centimeter. We also have initial open loop results here with GFZ software for rising occultation. Red and black are black as UCAR, red as GFZ results, so we have nearly identical results compared to UCAR, and also a very good agreement here to ECMWF. So we use this also for the derivation of water distributions here based here for cosmic, CHEMP, and GRACE data, which of course significantly increase the spatial resolution here to the CHEMP-only solution. We also have statistical comparisons of cosmic with CHEMP, so you know we have an improved characteristics in the lower troposphere due to the open loop, tracking 50% of the profiles reach the last half kilometer above the Earth surface, the same percentage, only 2 kilometers for CHEMP. So this is significant improvement for cosmic, but you also see in general we have a very good agreement, no bias for both satellites up to 30 kilometers, and also a very low standard deviation here to the ECMWF data of 1%. This indicates also a very high quality of the occultation data, of course. Applications, only some examples here. Near real-time data precision, GFZ also has 2 polar receiving antennas which will enable us to get access to the satellite data every 1.5 hours, because we have polar satellites. CHEMP is a polar satellites. At every 1.5 years comes again back to this antenna and sends the data down. And this allows us also, if we optimize all these communication lines, data transmission to Potsdam, and also the data processing, that we can provide all CHEMP data with a maximum delay of 3 hours. 3 hours between measurement aboard the satellite and provision of corresponding analysis results at the FTP server at GFZ Potsdam. This means you have to get the data down to the ground antenna, you have to get the data from Ionosphere to Potsdam, you have to generate a precise orbit, you have to generate the bending able solution. And this is done for all data from CHEMP within 3 hours. And this is the base also for the operational assimilation of CHEMP data, GRACE data too, at ECMWF. But here some results from cosmic, that cosmic and also other occultation data at the end improves the numerical weather forecast. So this is run without cosmic data. The blue line indicates the standard deviation here to a reference set from observational data, from radio sounds, and the use of the cosmic data increases the standard deviation of the forecast, and at the end it is a higher quality of the forecast. Another what we can do, we can use the Shemtape data to make visible if the ECMWF analyses are improved, or at least deviations to the Shem data are decreased. So what we plot here is a bias. It's, one can say, a mean deviation of ECMWF from Shem data from 2001 here to 2006. And this is some indication at the end how ECMWF temperature data deviate from Shem data. So we have in green a very good agreement. So globally, Shem is in very good agreement with ECMWF analysis. But several studies also have shown that ECMWF is not perfect, of course. So ECMWF started to assimilate cosmic data in December 2006. What we see is that the deviation to the Shem data significantly was decreased. So we have really no deviation. This is for us some indication that the ECMWF analyses are improved based on these use of the cosmic data. Also, the standard deviation is decreased significantly. So the Shem data, the Shem long-term data set is also a unique data set to compare with ECMWF analyzers.
In 2 or 3 you also have very low bias.
Yeah, you are right. But in general, I would see, and this is also a very interesting point, that you have an increasing bias here, so from minus to plus.
Yeah.
And this, of course, we have to investigate in more detail. But you are right, we have also zero bias here, but significantly such a modification of the bias we only observe after the assimilation of the cosmic data. And this can be not, how you say, there must be some reason. And this is obviously related to the assimilation. But you are definitely right. We have to look for this in more detail, because we also know we had solar max here in 2001, we had solar min here in 2006. So one possible reason, of course, is, and this we have to investigate in more detail, is there some relation of this bias structure or the standard deviation structure, but especially the bias structure, for example, to the solar cycle. But of course we do research, and this is one open point. But definitely we observe here some significant change of the bias, which must be in some kind related to the use of the cosmic data, of course.
James?
Yes.
For the number, can you give us an idea what on the regular basis, how many of the data, radio occultation?
Sorry?
What is the radio occultation data?
The radio occultation,
when they are put into the assimilation.
the radio occultation data here from Shem is about 150 profiles per day. And as I understand, in December they started with about more than 1,000 profiles, cosmic profiles per day. At that time, not in the lower troposphere, below 4 kilometers, they were conservative at this end, and also not rising occultations. That's why they started with these data in 2007. So the absolute number of profiles from cosmic was not too large. So I would also expect maybe a more visible effect also with respect maybe to standard deviation since 2007, I think November it was, when they also included the rising occultations from Formosat 3 and also down to the Earth surface. But here we only looked to 10, maybe altitudes above 6-7 kilometers here. So we did not include here the lower troposphere. But the most impact of the cosmic data to ECMWF is observed at higher altitudes. So we also have, and this was also a topic here of the presence of Professor Warner here. We had a workshop, Mosaic and Yagos on Tuesday. And we have done also some investigation and a recent paper. We compared CHEMP data with mosaic data. Not only interesting for air chemistry, also interesting for the validation of CHEMP and also for mosaic 3 cosmic data. The problem, for example, we have for the derivation of water vapor profiles in the lower troposphere is the separation of wet and dry term. So if you want to get water vapor from the occultation profiles, you have to put some additional information. This is our observable, and we have temperature and water vapor as the unknowns here, and we cannot resolve for this without putting additional information from ECMWF. But to learn if the water vapor we get from the profiles is something different from ECMWF, we need data which are not assimilated to ECMWF, and mosaic data are perfect for this purpose because they are not assimilated to ECMWF. So this is a unique chance to learn if our GPS-based humidity retrievals provide additional information compared to ECMWF. In the most cases, you only compare your water vapor profiles with ECMWF, but you get them using the temperature from ECMWF, and so it tells you not too much about if you have in reality some additional information. So what we have done, for example, are these humidity comparisons. We have not too many of them because you know the airplanes launch and land only at some distinct places here. So we found at the end 324 coincidences between such aircraft launches or landings. And this for the overall time period here from 2001 to 2006. We only use data here which were taken with not more time difference of 3 hours and a local difference of about 300 kilometers. What we see here is a comparison of the water vapor profile specific humidity of ECMWF, the model data, and mosaic and CHEMP data are very close nearby, at least in this altitude range, but significantly deviate from the ECMWF measurements. This means the observations are very close nearby, observations which are taken from two completely different observation techniques. And these observation techniques should you tell more the truth than the model here. And this is a case where we have such significant deviation, and also a case where we have an improvement, where we would have improvement of the ECMWF data, for example. The same I go down to detail here is shown for the reflectivity comparison. So of course a single case tells you only the information for the truth for one selected case. But to learn more on general, you have to do statistics comparisons, but also the statistics show you that we have on average in this altitude range above, maybe above between 5 kilometer and maybe 7 kilometer. A smaller bias here between CHEMP and mosaic measurements compared, for example, between mosaic and ECMWF. But we also have the deviations here in the lower troposphere, this negative reflectivity bias, which we also saw in the plots before. But in this altitude range, we probably could also improve ECMWF analysis if we would use water vapor data derived from maybe also mosaic 3 data, but also from the CHEMP data. So we also can compare temperature, but we find much more coincidences here because the temperature is measured from the mosaic airplanes also during the cruise. So we not have to wait until the airplane should land, so we have much more coincidences. And we learn at the end that the reflectivity agrees perfect, so we have no bias, minus 0.02 bias, percent bias, this is nothing. This means we have very good mosaic data and very good also CHEM data, I would say. But we learned we have a bias for the temperature, so we have to think a bit more on this bias. We have a bias of CHEM and mosaic data of about minus 0.8 degrees. And this is, of course, we relate this a bit more to the CHEM data, and we still are investigating. There's some paper published where we discuss these investigations. So you see the reality not always is perfect, not always agrees very perfect with the first shot. So we still have to look a bit in more detail to this investigation and to these differences here, and at the end also maybe to improve our retrieval. But we also know that ECMWF in this altitude range also assimilates a lot of aircraft data from other airplanes, not from the mosaic, but from other data. And this also is maybe a reason that mosaic agrees here very well, no bias with the ECMWF data. But of course, I want to focus here to this only because we think mosaic is a very valuable data source for GPS, for the validation of GPS radio occultation retrievals. This was demonstrated here for the first time with the CHEM data, but Formosite 3 data should be used with the Yagos data. Much more aircraft data, as I understand, will come. So what about its factor 5, or could you give an estimate how much more data will be provided by Yagos? It's a follow-on project.
And the goal is to equip about 20 aircraft.
20 aircraft. So we have for mosaic, I think 5? No, 3. So it's factor 6 or 7. So it's a significant increase of the number of also coincidences, because we also will have much more Formosite 3 data compared to CHEM. Climate. Tropopause here is keyword. A lot of you know on the tropopause studies. The tropopause is here a significant feature of the vertical temperature distribution of the atmosphere. CHEM data, but also Formosite 3 data can be used to very precisely locate where is the tropopause, in which altitude range. For example, because we have a very high vertical resolution, this is also a single case, a radio sound, so a weather balloon. Here, these red dots, you have some wave-like structure, and this is also very precisely here given by the CHEM data. And the models don't give you such high vertical resolution, so this is some significant advantage here of the radio occultation data. The tropopause altitude can be derived on a global scale, so you also have some activities, and this is also a point of our cooperation here, that we want to look in more detail to regional characteristics of the tropopause. But here, global investigations and the use of the additional use of the cosmic data increases, of course, significantly the spatial resolution of such investigations. What we see here is a global view of the tropopause altitude of about here 17 kilometers in the equatorial region, via about 11-13 kilometers in the mid-latitudes, up to the polar regions where we observe the lowest tropopauses down to 7 or 8 or 9 kilometers. So we have a tool here to monitor the tropopause altitude, and the tropopause altitude, if we monitor it on a long-term scale, also is more and more recognized as a tool to detect climate-relevant changes of the atmosphere. So assuming a warming of the troposphere means extension, we should observe an increase of the global mean tropopause altitude. And this is what we have done here in a study, which is just in print from GRL. It is a first investigation which shows that we can demonstrate an increase of the global mean tropopause altitude using the occultation data from CHEM, which is about 180 meters per decade. And this agrees very well with model simulations here, for example, by 1000 at I from 2003. So atmospheric physics, we also have some activities regarding such wave-like phenomena, and so gravity waves. There's a lot of publications done. Also the CHEM data, red color means here large amplitudes of such waves, and we also can significantly increase here the data, the spatial resolution of such gravity wave characteristics. This is some kind of energy of these waves which can be related to the amplitude, for example. And here also several long-term investigations use the CHEM data set to derive such wave-like characteristics. So you may ask why it is important. It is important because, as I understand, ECMWF or other meteorological models don't take into account these waves. You know it much better than me. I'm not so a meteorologist. But this here, such investigations could help to provide such information for the assimilation, because such wave phenomena are significant and should be taken into account for atmospheric investigations. We also started some investigations on ionosphere. So we use CHEM data to derive vertical electron density profiles. We are in good agreement here with UCAR and also data from German Aerospace Center, but also here with in situ data. So we have a device about CHEM which gives you precise information on electron density at the orbit altitude. It also agrees very well, and we use completely know these data here for the GPS retrievers. An interesting phenomena which can be observed in the lower ionosphere are the irregularities, sporadic E-layers. This is some other, so we have a PhD student working on this. We can use, for example, the 50 Hertz data from CHEM cosmic, but also from GRACE cosmic here. The profiles go up to 120 kilometers. In the most cases, you only see how the data behavior is in the lower troposphere, but you also could ask where stops the data. The data stops from cosmic at 120 kilometers. So it covers the range of about between 80 and 120 kilometers where these irregularities occur. So we have also a good tool to detect such irregularities, which at the end also influence, for example, telecommunication. It's sometimes disturbed, sometimes not. But this also can be related to such irregularities. So, and we used the data to derive such cloning characteristics. So we have here occurrence frequency, so this means 50% means every second profile shows such phenomena. So this means it is significant behavior in this region. So especially in this region, for example, causes the accuracy of navigation satellite systems could be degraded. So all these things can you learn from such measurements. And we also see, and this is also a GRL publication, this is very close to a publication now, the first time the signature of the magnetic equator. You could not show this with the CHEM data. It's for the same months, October to December 2006, because the resolution is much worse. By quality, it is the same. So we have a maximum here, we have a maximum here. But we have a much more finer spatial resolution. Here we cannot see this, but here clearly we see the magnetic equator. And this was first shown here also with the Formosan 3 data. So a new branch of research we opened for about 3 or 4 years is GNSS Reflectometry. We have some initial results. 2 years ago, we had such ground-based measurements. So we put a receiver on this Fahrenberg here in the Bavarian Alps, and in parallel to the direct signals, we recorded here reflected signals from sea surfaces. What we can do with these signals, we can do some altimetry. We can monitor the changes here of the sea, of the lake surface. And we can do this with an accuracy of about 2 centimeters. Already with these ground-based measurements, with these initial results, so this is some perfect, this opens completely new perspectives for remote sensing. So applications are here altimetry, and of course, on the other hand, I will show it in the next plot here. So this was altimetry, but this is more details here only because you have to someone combine the direct with the reflected signal. This is some correlation plot here, and you see here the correlation for the direct signal, and here for the reflected signal. From the shape of this correlation at the end, this is related to wave characteristics. And wave characteristics here, we can correlate to wind speed. So if we know the shape of this line here, which we can at the end get from such kind of measurements, we can deduce to wind speed. And this is also would be a very new technique for satellite-based Earth observation. So we are quite close here already to such results. And some prospective, of course, for such kind of measurements is the application aboard satellites. So they have here some simulation results for all 3 navigation satellite systems. For example, 48 satellites equipped with GPS receivers for GNSS reflectometry could provide a nearly complete global coverage within 15 minutes. If you could establish such system, it would allow you parallel monitoring of the complete ocean surface with some important application, and this is the background here of this system, of this investigation, to detect tsunamis. So you know maybe that Germany has some activities to develop a tsunami warning system, and originally it was thought to put a second, the first step is a ground-based system, the second base should be a satellite-based system, which probably will not be funded, but we have done some preparatory investigations, maybe we can fund it from other sources, of course, and to get such system for the detection of tsunami waves. But even with 18 satellites and 16 planes, we get already a very good coverage. So, but this is some future, definitely we believe some future trend, because it's not only a fiction, we already observed, this is a GGR publication here from 2002 from our group, we observed already such signatures of reflected signals in our occultation data from CHEM. Blue are occultations without reflection signatures. Red are occultations with reflection signatures. You see only above ice surfaces and oceans. And if you look in more detail here, if you take an atlas, a map, then you see exactly here lakes or Caspian Sea, for example. So you only can observe, of course, such signatures above ice and ocean surfaces. So this is not only fiction and maybe something nonsense. This is already was shown with the CHEM data. So some activities for future projects. Of course, the future is Galileo. In more detail, I would say the combination of GPS, the modernized GPS, with Galileo and, of course, GLONASS, but in the first step, maybe GPS and Galileo. Galileo is a new European navigation satellite system consisting of 30 satellites in space and a large, of course, control segment on the ground. And a lot of battle was done. It was very difficult to come now to the decision that it will be funded, because every country, of course, wants to get some share, some money to have some important influence. But at the end, it was a long battle. But at the end now, it seems to be that it should be an end. So we have already, this is also not only a fiction, we have already 2 satellites in orbit, G over R, G over B. G over R has, in addition to G over B, a laser retroreflector and a much more precise atomic clock about. So G over R was launched already in 2005, and you see here you have 2.5 years difference. Originally it was planned that G over B should be started already in 2006, in early 2006, but due to this financial difficulties it was postponed to 2008, but it was around 1 month ago. The second satellite of the Galileo system is already in orbit now. GFZ has some contribution also to Galileo for monitoring the satellite, the signals of G over A. Actually, some ground network was established here, and we contribute with 4 ground stations: Mitsuzawa, Wuhan, Dunedin, and La Plata. This is our global network operated by GFZ. 4 of GFZ stations are equipped with Galileo receivers. As you see again here, Mitsuzawa, Wuhan, Dunedin, and La Plata. These 4 stations contribute to the global network from ESA to monitor the signals of G over R. But here we only are in the role of a more or less data provider. So here is such a station. It's a quite large station, quite a lot of effort also has to be done to take such measurements. And GNSS receivers, we have also some activities on GNSS receivers here. We have, of course, if you want to do occultation measurements about the satellite, you need a GPS receiver, and of course you have to put the GPS receiver to the satellites and to integrate the electronics, which is very complicated, to the satellite bus. And we have experience here for Chem, Grace, but also for Karazhan X with 2 different US receivers. But we also learned during the last years that there is some limitation if you have control, for example, of the source code of the tracking software. Because GNSS or GPS is not designed to do remote sensing. It is designed to do positioning. And to do remote sensing, you have to optimize your receiver tracking software to get maximum information content, and this you only can do if you have access to the source code, for example, of the receiver. So we started some activities here, single frequency receivers built by GFZ, the open GPS community, to integrate also occultation and also reflection software, but we also have contact here with a company, with Jared, to start also implementing here such algorithms. The advantage here should be that you can make use of much more cheaper receivers for putting them to new satellite missions, and especially to micro to small satellites. And this is a real advantage of GPS. You have here a remote sensing tool, a sensor which is very small. So you can put lots of satellites which are very small to orbit, and put GPS receivers on them. Here some ideas. Cicero, 100 satellites to establish such constellation. A constellation of 100 satellites would give you a continuous spatial resolution of temperature measurements, for example, for a distance of 100 kilometers, continuously. And this is a new quantum jump also for, I think, weather forecasts on a global scale, but also on a regional scale. But these are some future thinkings here. And definitely we think, maybe not by GFZ, also by Taiwan, by US, or by other countries, we definitely will see such activities in the next years. So we also, some example here, our receiver is also capable of tracking new signals. So we have not only more satellites in future with Galileo, we also have new signals. And new signals, for example, L2C, means a much more stronger second frequency. all which are involved in data retrieval with the occultation data know that we don't make use of the second frequency in the lower troposphere, but with the new signals here, GPS satellite 17 is already a modernized GPS satellite which provides such signals, such new signals. We can improve the data quality. And we have used this new signal here also for this altimetric measurements with the same result here, with the same accuracy of 2 centimeters was shown before. And this is the first demonstration of this new signal for remote sensing. So we have also some activities to put, of course, step by step, ground-based measurements, then airborne measurements, and the first step, slow-moving airborne platforms. The Zeppelin NT is an airship. We have a close cooperation also with Professor Warner. He, in parallel, is doing air chemical measurements, for example, so we share the costs for this experiment because it's quite expensive to rent such airship for a measurement campaign. So we do first measurements in October here, and in parallel we also install a GPS receiver here aboard the German research aircraft Halo. And this is a plot which I have shown already at the Mosaic or at the Ionosphere workshop. So, of course, the next step then should be commercial aircrafts. And if you put such receivers to China airline aircrafts, because as I understand they are very cooperative, they support such kind of activities. You can combine this formula that follow on. Maybe we think in the future in Galileo and GPS, it could help, of course, for our activity. It could be a very unique database can be formed here. Including also this reflection stuff, not only on the Earth surface, but they also have to propagate 2 times through the atmosphere, ionosphere. So also probably in future we can derive from such reflection measurements information on atmosphere and ionosphere, which was demonstrated already in several studies. We also have some ideas on future satellite missions. So one idea is here nano, the GEM, to put GPS receivers on small satellites and to put them into orbit and to do at the end reflection and also occultation measurements with a core instrument here, GNSS receiver. So the ideas already in the more details, these plans, but of course the most important is at the beginning to get the money, and they are, it's initial results 20, 20, 20 to 30, 30, 30 centimeters, this cube, so quite small, but it is a very initial proposal to get the money. But this can be, of course, be modified during the course of this project here. Main mission goals also should be, of course, in GNSS atmospheric sounding with 6 satellites and also application of reflection measurements. So these are here the sub-points of these reflection points, and also some space geodesy, so for highly accurate geocentric reference frame. So it's not only a vision, a part of this is already reality. So this is a system here for global atmospheric sounding using GNSS, ground-based, regional and global networks, but all components, airships, aircrafts, but maybe also ships, buoys, up to satellites using all the signals from 3 navigation satellite systems, Galileo, Lunar, and also the modernized GPS in future. And this will allow us to monitor the global change, so to get a global view to the Earth's atmosphere, for example, climate here, we saw some applications, weather, improving the weather forecast, monitor natural hazards, warning systems are some keywords here, gravity waves, tropopause for atmospheric physics, but also space weather, ionosphere. You have also here in your university very active persons with focus to this research, but also reflections allow us probably in future, for example, also to monitor the sea surface ones. So this was what I want to do here also as a bit thank you that I could be here. I enjoyed it very much the time. I'm a bit unhappy that I have to leave tomorrow, but of course I'm happy also because my family is waiting for me. And, so I'm this one, I'm not so okay to go, and I'm a bit okay to go, of course, but I come back already in October to participate in the Formula 3 workshop, but also here to NCU to give some lessons within the atmospheric school. Okay, thank you very much.
Any question or comment for the
So I know this is recorded by video.
Yeah.
So it would be interesting also to have this video. So you have it, is it digital video or digital?
Yeah,
Cassette?
digital.
Okay. Oh, good.
I really enjoy your talks. So can you say a bit more about the strategy, about the early warning system, the strategy of the monitoring? The part, because of the
Yes.
some of the part, I think I understand a little bit. How about for the early warning part?
But this is
strategy.
I told this is a vision, I would say, because we currently have, as maybe it is, I don't know how many details you know, but when this large Sumatra tsunami was in 2004 during Christmas, so the German government gave some significant amount of money, I think it was 50 million euro or so, to develop a ground-based tsunami warning system. And this works on base also of GPS stations, which monitor the earthquake, and on some buoys, which should monitor the wave. Because the wave is only 60 centimeters, and so you should monitor also the tsunami. So there are some earthquakes, but you don't get tsunami. This is the current version, and this should be, I would say, operational in October. In October will the German Chancellor Angela Merkel, she will go to Indonesia to give this system to Indonesia. Part, and now I come to your question.
So for the ground-based,
This is a reality.
Space-based.
Yes.
I'm sort of asking about the space-based.
Yes, this is now the second step. Is a space-based system, and the space-based system was originally foreseen as a second step to this system. Very probably we will not have a second, because it's also for Germany a lot of money and difficult to get. The idea was to put a satellite, a multi-satellite constellation equipped with GPS receivers, and of course in such density that you can get the data very quick to the satellite, of course, and also very quick to the ground. So this was the core strategy, I would say. More details I cannot say to you because we had not too much more investigations on this. We only had this simulation study. This is a part of the first stage of the tsunami early warning system project, and also the receiver development. And probably we will have problems to continue funding for this. But the idea is very simple. So put a lot of satellites into orbit, get the reflected signals, get them very, very quick down, and then you can do a tsunami warning system. It's very easy, but of course very difficult to put into work, because also the technology, how to record the signals, the reflected signals aboard the satellite is very difficult, and also the data analysis. So it's something for the future, but it's definitely, it should work. It should work, because our initial results indicate that it should work. But that's why I think it is now, it's a moment, it is a point for researchers, for us. And we should push these things. And I would not see an operational system maybe before 10 years or so, seriously spoken.
Okay.
say we are not happy because we are going tomorrow. Again, we are very thank you very much for this very much presentation. A small question is, what is the highest altitude we can get for the temperature retrieval from the GPS technique, and how is the accuracy, especially in the altitude above 10 kilometers?
Yeah. Well, this is a very good question. There exists some plot on the accuracy.
No, not here.
So I think this is somewhere this. So this is altitude. Maybe here is 25 kilometer, and maybe here is, let's say, 8 kilometer. And this is the temperature error. And this should be about 0.1 Kelvin. I don't know, maybe here 1 Kelvin, and so on. So this is some very famous plot. The highest accuracy, so the smallest delta T, you should get in the altitude range between 8 and 25 kilometers. Below you have inference as multipass or so, but I see here in future some reduction due to the application, for example, also of the new signal structures. And we also have ionospheric inference above 25 kilometers. Here I would simply answer your question, the most precise you are here in this range, and if you come more up and more down, you would get more and more unprecise. But I would say the new missions, for example, METOP satellite has shown that he has better signal performance even here at higher altitudes. So maybe for METOP could be that we can put such line. So this would mean we are a bit more precise at higher altitudes, so smaller delta T, maybe for METOP, compared to, let's say, the delta T maybe from CHEMP also. So we should be better in the future, I would say, but maybe not significantly. And also, as you know, METOP, they also have some problems with the data processing. This is the other. So they have a better receiver, but they have not so advanced data processing. So maybe for the future we should be better, but I would not to be too optimistic, for example, to get temperature information at 60 kilometer altitude. 60. I would not be too optimistic. I know that a lot of people, they plot data up to 60 kilometers, but you know we have, because the data quality here is not very good, so you have a lot of noise, and what you do to reduce this noise, you include additional information from, for example, climatologies or so, and what you measure at the end at 60 kilometers is, of course, in a significant share maybe climatology also. So some people do not tell the real truth, I would say. So we should realistically say we are very precise here, and it is definitely good to put some effort to be better here. But we are still, we have to accept that we are here not so good, I would say.
Okay, one more.
One more question is, my understanding is you have developed your own retrieval algorithm.
Yes.
Compared with the one developed by America.
Yes.
So would you like to make comments to compare the advantage of your retrieval algorithm to the American?
I think it is more or less the same at the end. So the basic principles are the same. And for example, we currently have an international study comparing retrieval results from UCAR, JPL, and GFZ. From the raw data level, we found for CHEMP data for the time interval from 2001 to 2006, we found a mean bias between UCAR and GFZ retrievers between 8 and 30 kilometers of 0.001% in reflectivity. So this
Almost identical.
is almost, I think it's more or less identical.
Yeah, here related comparison is somewhat sharp.
Yes.
And here send you the related information.
Yeah. So I think the basic principles are the same. Of course, we have some other software. It was made more and more perfect during the years. UCA has their own software which was made more and more perfect during the years. But we, of course, this is a mean deviation. Of course, we also observe some differences, but we look in more detail to these differences. But in general, we have very, very good agreement, which is also, I think, a promising sign for this occultation technique. So you have different groups which analyzing the data, and at the end they could, if they do it very carefully, they could get the same results.
Okay, any last question goes to the students? Any student? No. You
are not student.
Other younger. Okay. No younger student. Would like to ask? Okay.
Okay. So usually we consider the refraction, the occultation points, but you are talking about the reflection.
Yes.
So how can we avoid that reflection? Usually in occultation we want reflection only consider. Again, GPS occultation,
yes.
We take the bending angle, that is like a refraction.
Yes.
Refraction and
so you mean
reflection.
here, this is GPS,
Yeah,
and this is maybe CHEM.
yeah, yes.
So you have here,
It's like a
the bending here is the Earth, and what here?
Yeah.
This is your occultation point. And the reflection point is very close. This is coherent reflectometry. This is what we can do with the occultation antenna. We can do this. This would allow us to do this altimetry. The second is incoherent. This means to record the waveform. There we would need another additional antenna from CHEM, which is looking to the nadir. So, and this of course we need another GPS satellite here. This is another system. So we have two different techniques how to do reflectometry. I not wanted to go to this here in the detail here, but for CHEM we have done this coherent reflectometry, which we can do with the occultation antenna. Even with this, if we would optimize the receiver a bit, I would say we could do very good altimetry monitoring. There is a study in GRL from the JPL. People, they had done using this technique a decimeter, I don't know, maybe 50 centimeter accuracy altimetry of Antarctic ice shelf it was. Even this receiver which was not optimized for this kind of measurements. But in future we also would see this, but this requires a larger antenna. So maybe for our system, but this then you have of course very carefully to take into consideration that you can use already such occultation-like geometry for such tsunami warning system. But this is point of investigations, I would say. Because we have only, I think, one satellite or one space shuttle flight where such a nadir viewing satellite signal was recorded. So this is difficult. But this was demonstrated already that it works quite good.
Yeah, I think the time, over so much. We want to thank you again. We already going to have a welcome party for you. Then we have another farewell lunch party for you at Wickert. Everyone, feel free to join this lunch at Wickert. Okay, and right away. Yeah.